hard and fast change in the course. Right? So for the next few weeks, it's really going to be a class in finite element analysis. Who's had a class in finite element analysis? Okay, so a couple of you. The first few weeks probably be really easy review, but I approach it a little bit differently. I know I don't know exactly, depending on where you were taught finite elements. A lot of times, finite elements are taught, especially in mechanical engineering, or maybe even in civil engineering too, as sort of they're introduced as sort of a matrix methods and structural mechanics. And then, if it's an undergraduate course, that may be all you ever do. If it's a graduate course, then halfway through the semester, at some point, you'll start talking about the so-called weak form and the variational interpretation of the equations and all that. Okay, I do that right from the beginning, so I never sort of look at this as a matrix methods and structural mechanics. I mean, finite elements are a way to they're a way to solve any partial differential equation boundary value problem, and the physics doesn't matter. If you have a partial differential equation, it's possible. It doesn't matter if it's a heat transfer problem, a mechanics problem, a diffusion and porous media problem. If you just follow the same steps, and we'll talk about what those steps are. If you just follow the same steps, you can use the same method essentially to solve all of those problems. Okay. I shouldn't go that broad. If you try to solve incompressible Navier-Stokes equations without some little tricks, then you're going to have some problems. But that's because they're nonlinear, right? Anyway, okay. So, finite elements is basically a way that we're going to take some complex thing, right, like an engine, right? In this case, I prepared this lecture when I had taught this to mechanical engineers. So some of the applications will be mechanical engineering related, but again, physics don't matter. Okay, we're going to use the finite element method to solve a couple poor elasticity problems in this class. Okay, but you can, the idea is that we have something complex that we clearly, if we wanted to solve the coupled, heat transfer and deformation equations for, say, the cylinder walls or the cylinder head in that engine, we don't have an analytic solution for that. It's too complicated, right? So what we can do is we can take that engine and we can break it up into little tiny pieces, and over each of those little tiny pieces, we can approximate the solution and solve for it. And basically then we just assemble through through continuity and a method of superposition, we just assemble all of the tiny little equations into one big set of algebraic equations, and we can solve for it, okay? By the way, this is not a cartoon. I had a colleague that gave me these images. This was an engine at GM, and this is the mesh. I know it's a little bit hard to see, but all those little lines. This is a mesh associated with that engine, at least the long block. So those are the cylinder heads there. And just this mesh right here represents months of work just to create the mesh, not even to solve the problem. And in fact, this is typically the case in finite element methods. It usually takes longer to create a good mesh than it does to solve the problem on the computer. And so, so GM will have contractors that their whole job is to just create these meshes. And we won't talk about it in this class, but sort of the new wave, the frontier of analysis is to actually use, so that the mesh is created separate from the CAD drawings, the computer-aided design drawings, that were used to then machine this engine. And so the sort of new frontier of the wave is to actually use those CAD geometry directly in the analysis, and this is the so-called isogeometric method. And so we won't talk about that here, but nevertheless, that's mainly aimed at reducing this months of work associated with creating a mesh. Yeah. Well, I'll talk. Mesh will be really clear here. So it's a discretization. Okay. So it's how we take this complicated thing and break it up into little simple things. And then in this class, those little simple things will be triangles or quads in 2 dimensions, or tetrahedron and hexahedron in 3 dimensions. And in fact, we won't ever even do anything in 3 dimensions in this class because it's a straightforward extension of 2D. Okay, so in this class, the discrete things we'll break them up into will be triangles and quads. Right? So a quad is just a four-sided parallel pipe thing, but not it's not necessarily have to be a trapezoid or something that the sides can be. So it's got 4 sides, but they could be kind of arbitrarily oriented. Okay? So there's a little bit of philosophy in this lecture. You know, this is normally the lecture I'd give on the first day of a finite element course. Right? So I always like this quote, the purpose of computing is insight, not numbers. And this is the book dedication in Hamming's book on applied numerical analysis. So you probably all know Hamming, even if you don't know him. There's a famous book, series of books called Numerical Recipes, right? So if you've ever, numerical recipes in C or numerical recipes in Fortran. So if you look like in MATLAB or something, if you were to look up the fsolve, if you went and looked in the source code, and we just use fsolve to do a root solve, right? If you went and looked at the source code, I think it uses Brent's method, which is a combination of secant and Newton's method, and a combination of a bisection and secant method. And if you looked at the implementation, it's probably 99% following numerical recipes in C. So a lot of the sort of standard algorithms that we use for interpolation, for all this, are in this series of numerical recipes books. And they're still, even though they're old, they're still very useful. So that Hamming was the author of that book, and I always like this quote. And the idea is that with all the uncertainty in engineering design and analysis, really the purpose of, and I guess I should go to the next slide, is I sort of prefer to kind of change it a little bit and say the purpose of analysis is an insight, not numbers. So that's really what we're doing in this class, analysis, okay? And with all the uncertainty in engineering design, it's very difficult to have exact predictions, okay? And so a lot of times what we use computing for is to understand trends or other things, and so just to gain insight into the problem. Now that's not to say we can't be predictive. In many cases, we can be very, very predictive, and even in the face of uncertainty, we can be predictive within error bounds if we do things carefully and we use uncertainty quantification. So we can still give an answer in the face of uncertainty, but it's not going to be a deterministic answer. It's going to be a probabilistic one, right? So we can give an answer with confidence bounds, okay? And as time goes on, our ability to be actually predictive is more and more. So it gets better and better, okay? But at the heart of all this is really insight, okay? And so just, again, there's some philosophy here. What is analysis? Well, it comes from the Greek word analyin, and that means to break up. And I think that's really kind of cool in the context of finite elements, because this is exactly what we're going to do. We're going to break up our complicated problem into a bunch of small problems that we can then assemble and solve together, okay? But an informal definition in the context of science and engineering would be to probe into or simulate nature, all right? So why do we want to do analysis? So analysis is the key to effective design, okay? And again, I prepared this lecture in the context of sort of mechanical engineers. So you're designing an airplane, you're designing an engine, right? But we also, in petroleum engineering, we design things, right? We design a reservoir, in a sense. As a reservoir engineer determines how to most effectively drain the reservoir, and it's part of that we design completions, right? So we do a lot of design in petroleum engineering. So what is an effective design? Question. What is an effective design? So, well, we don't just want to simulate the real thing. We want to use that simulation to make decisions, right? So, and then based on those decisions, we want to alter our design in some way, right? And so ultimately, in the context of like a reservoir, I mean, an effective design would be the one that drains the reservoir, that gets as much oil and gas out of the reservoir as cheaply as possible, right? But the sort of bare minimum definition for an effective design might be one that works. Right? Needs to work, right? Sort of a necessary condition for a good design, but is it sufficient? Right? So let's have a little fun. That mechanism got the car to move, but is that the most effective way to do it? So maybe not one that works. Let me stop this. Rube Goldberg machines are kind of fun. So one that performs the task efficiently, right? One that's economical. So the idea here is, you know, if we needed a metal that was ductile, you know, easily deformable, so that we could mold it into some shape in a machine, in a manufacturing process. Gold certainly fills that requirement, right? But so does copper. So wouldn't it be better to use copper if it, you know, gold is also very, very inert. That's a nice feature of gold. But if you could get by and you didn't need the inert properties of gold, then copper fills all the sort of other requirements for a easily deformable metal. So let's choose copper because it's going to be far more economical. Safe, this is important, right? This is the famous Alaska Airlines that the fuselage actually ripped off while they were flying. And I think this was in 1980 or something. Thankfully and unbelievably, no one was hurt in this. But obviously, I wouldn't want to have been a passenger on that plane. One that's manufacturable. So here, you know, again, I have a picture that sort of an assembly line in a car manufacturing facility. But in terms of, we also have manufacturability in petroleum engineering applications. For example, we can use our models to design completions, very complex completion processes that might not actually be realistic to do, you know, in practice. And so this is a sort of manufacturability aspect that we have to keep in mind, that, you know, just because something looks promising when we do analysis in the computer, it doesn't necessarily mean we can actually in practice implement it. And this is not so much important for petroleum engineers, but you know, sometimes we want our designs to be appealing. Certainly, if you're an automobile manufacturer, and you know, even Apple, of course, is famous for their industrial design. The products do look appealing, right? So in performing analysis, we sort of take whatever the physical system is, and we design a mathematical system. So usually this involves some engineering intuition about what the important physics are, and then we use our knowledge of physics to come up with a mathematical equation that represents the physical system. And so let's look at an example from solid mechanics. Okay, so this is just a 1D bar, and we're actually going to write our first finite element code that we're going to write in this class is going to be for a 1D bar. So we'll start with this guy. And we actually already know the equation, the conservation momentum equation in 3D, and we could just write it down, just lower the dimension of the problem. We could just write it down and start there. But it's not too difficult to also just derive the one-dimensional equation directly here. So we'll do that. So we have a bar, and whenever I talk about a bar, the nomenclature, the language here is, when we talk about a bar, we talk about something that only has axial deflection, okay? We won't talk about them in this class, but also in finite element analysis literature, a lot of times you'll hear beam. So a beam is something that doesn't have axial deflection, only has bending. Okay? And then also you might hear about a frame. Well, a frame is something that has axial deflection and bending. So here we're talking about a bar. It has cross-sectional area A, Young's modulus E, length L. We're going to apply a load P to the end, and we're interested in the deflection along X, where of course this is the X direction. Okay, and so, I mean, you might remember from solid mechanics, if I were to just pull this a distance delta, right? There's a closed form equation. Delta is equal to what? If delta is the displacement of the tip, yeah, it's PL over AE, right? Okay. But if we look at a bar that's possibly even has a varying cross section, and we look at a little differential element, it's the same problem, it's just now we possibly have a varying cross-section. If we look at a little differential element, and we just write down Newton's second law, right, so we're going to have some force acting on that side, some force plus the change in force over x dx, right, where this distance is dx. And then we just write down, so the sum of the forces. So the sum of the forces are minus F plus F plus is equal to, no, on the right side is, we're talking about MA, right? So M is the density times the area times dx, right, times A, which is the second time derivative of displacement, okay? So the dx's cancel, the f's cancel, and in this case we'll go ahead and make the assumption that inertia is negligible, so we'll just get that term to go away, right? So we basically have partial x f is equal to 0. Well, F, in terms of stress, is the stress times the area, right? And we have if we use Hooke's law, a constitutive model, then the stress is equal to the Young's modulus times the strain, right? Times the area. And then we have a mathematical definition for strain too, right? Strain is partial U partial X times the area. So if we plug that back in, then we have partial X E A of X partial U partial X equal to 0. So that's our equation of motion. Can we solve that guy? What else do we need to solve it? We need boundary conditions, right? So on the left-hand side, so U at 0, at x equal to 0, we have that the displacement 0 because it's a fixed, okay? And on the right-hand side, we basically we have that the stress, right, or rather the force on the right-hand side, which is the stress times the area, and the stress is the Young's modulus times the strain. So if we write it down, the stress times the area at L is equal to P. Right? So that's our boundary condition. So there's our differential equation. It's an ordinary differential equation because it would have been a partial differential equation if I would have kept this term, but it's an ordinary differential equation, right? So this one is actually simple enough we can solve it by hand, right? Does everybody remember the method of undetermined coefficients from differential equations? Yeah, I remember it too, but I'm not going to do that. I'm an engineer. Whenever I'm faced with a differential equation that needs a solution, I open Mathematica. I'm not going to waste my time. I'm not trying to show everyone what a great mathematician I am. So Mathematica can actually solve a differential equation in closed form, right? So at the top, I just have an area function that I just plotted. In this case, it's just a rectangular beam, right? And so then my differential equation, the only difference is I say that, and it helps later, that my area is the half cross-sectional area. So then my equation of motion has a 2 there. But other than that, it's fine. It's just because I want to define, later on I'm going to define more complex shapes, and I'm going to define them on one side, essentially. The function will be on one side, and so the cross-sectional area is double that. So other than that, it's just the same as what we just derived. The equation of motion is, and that's defined here, okay? And we can solve that using Mathematica's dsolve. And so you can see that for the rectangular case, u is equal to px over a ey, right? And so at x equal to L, we get the exact undergraduate solid mechanics known solution, right? PL over AE. But there, we also have a solution for all of x, right? For the displacement across the whole bar, so that we can plot the displacement as a function of x anywhere, right? And we can also define, so I have some area functions up here. Oops. So I can also go to something more complex. Like, so if I have this kind of shape, then I can actually solve, and this is the analytic solution to that shape, right? It's the analytic solution to the displacement. And you get a field that looks like that, right? And I just, for fun, created a little tool that you could sort of examine all of these. So if you go in here, you can choose a uniform area. You can choose linear. So there we go. So you can choose it to have linear, and here's your displacement profile. And I have, P and A, and these are all variables, and you can see how it changes the solution. And you have even this funky sinusoidal thing, which we can compute an analytic solution for. Okay. But what if A is non-uniform? What if A looks like this? Now what do we do? Well, we might be able to interpolate this curve to some extent and do exactly what we did. But we can also break the thing up. And it's a little bit hard to see, but there should be dashed lines here and here and here. And if we do that, now you see that we have things that we know, right? These are all those scenarios, right? This is a uniform, this is linear, this is that funny sinusoidal thing, and this is a quadratic, and that's an extension of that quadratic curve, right? So these are all things we know. We have analytic solutions, and we can write them down. Therefore, we can use the principle of continuity and superposition. So continuity would only mean that in the solution across this distance, I just have to make sure my boundary conditions are consistent, such that the displacement at this point is continuous. I mean, it has to be the same as the displacement there and there, right? So when I solve all these, I need to ensure that my boundary conditions are correct. But then I can use those known solutions, okay? So this is sort of what is at the heart of the finite element method. So in the finite element method, we take a domain and we break it up into little subdomains, and we call them finite elements, okay? And so the collection of finite elements is the finite element mesh, okay? And over each finite element, we approximate, and this is the key difference between what I just showed and what we do in the finite element method, is that there we had analytic solutions. But in the finite element method, what we do is we approximate the solution by functions. And typically we use polynomials, but they can be other things, okay? And then from that approximation, we can write down a set of algebraic equations that we solve at selective points. These are called nodes. These are typically the corners of the finite elements, okay? But it can also be other places in the middle of the element or along the boundaries, just depending on the order of the element, and we'll talk about that. And then what the last thing we do is we assemble all of these guys using continuity or balance of physical quantities, and we solve the system, okay? And so, again, notice I said approximated. So what we typically do is we say that the continuous solution U is approximated by some U of H that is the summation of some unknown UJs. So these are really what we're solving for. These are the displacements. If U is a displacement, right, then we're talking about the displacements at the J nodes times some functions, okay? And these functions are called basis functions or shape functions, but these are our approximation of the continuity of the solution across the elements. So typically we'll just use linears. We'll see a case in this class later where we'll also need to use quadratics to meet something else. And then you can, in general, have another term over here where these CJs are not necessarily, they're also unknowns, but they're not associated with the nodes. And then you can have your own set of functions. And typically this is used in the so-called extended finite element method or generalized finite element method. And these FEAs are so-called enrichment functions. So this is in the case where you know more information about the field, about the solution of the field, and you can then enrich the solution even more than you would just with a polynomial, right? So there are some sources of error in finite element analysis. One of them is due to discretization error. So this would be that we're taking a continuous domain and we're representing it by a collection of finite elements, and so there's always going to be a small amount of error associated with that. Now, thankfully, as long as we have a big enough computer, we can make that error small. So that I'm just highlighting the regions that we're missing because of our discretization. But thankfully, we can make this error very small by reducing the mesh size. So here I have a fairly coarse collection of triangles, but if I were to have much smaller triangles, then I could represent the boundaries of this much easier, okay? And like I mentioned at the beginning of class, now there are ways that we can actually represent through this so-called isogeometric analysis. We can represent the boundary of the thing exactly. And then there's really no discretization error in that case, okay? But we can always reduce discretization error by refining the mesh, because as I get smaller and smaller elements, then I can conform to the boundary better and better. But that is a source of error. We can also have a source of error due to the approximation. So again, if the real solution is quadratic, but then I choose a linear interpolant over the element, right? Then the difference there is going to be the error, right? Okay. And now again, I can reduce this. I could reduce this by choosing more elements. So if I have more elements, I could fit that quadratic curve with, say, 2 linears a little better, right? And I could fit it even better with 4 linears, right? So I can reduce it, or I can fit it exactly with 1 quadratic, right? So I can improve. I have sort of 2 methods to improve the solution in finite elements. I can improve it by using more elements, this is so-called H refinement, discretization refinement, and I can also improve it by using higher order interpolants. So in this case, if I just, instead of using a linear interpolant, I use a quadratic interpolant, with 1 element I can match the solution exactly. And of course, there's always computer-related errors. We solve these equations on finite precision machines. Of course, nowadays, this is really not a big issue. We have 64-bit machines, and it's very rare that, I mean, it still happens under certain scenarios, but it's very rare that numerical round-off causes problems for us more than the truncation error and the discretization error. So, again, after we assemble the set of equations, we end up with a set of equations that are algebraic, and in the case of an ordinary differential equation, it's really just an equation like this, where K is a matrix, you have some unknown vector of displacements U, and you have some right-hand side vector which contain the boundary conditions B. And so the solution to that, of course, is just linear algebra, is K inverse B, okay? One issue, though, is that K, without imposing boundary conditions, K is singular, so you can't invert it. So we have to impose the boundary conditions so that we can invert this and solve the problem. Of course, then the last step is, if you're solving time-dependent problems, then you truly have a PDE. This is the case if you've undergraduate in petroleum engineering, you took a course in reservoir simulation where you solve a diffusivity equation. That's a PDE, right? So you have to discretize in space and time. And usually what's done is that we discretize in space via finite elements, and then we just discretize in time via finite differences. Okay. So just a few more slides. These are commercial software, popular commercial software that analysis, FEA analysis typically done with. There's Abacus, ANSYS, Nastran, Elastina. There's also many open source software and frameworks to write finite element programs. We typically package that. We would combine it with some type of CAD program. So this is more specific to mechanical engineering, where you're drawing something that you're going to be analyzed. In a petroleum reservoir setting, if you're talking about a reservoir, you could import sort of point cloud data and use automated tools to build a discretization from that, from the reservoir. You wouldn't necessarily be drawing it by hand. And then there's also dedicated meshing tools. Sometimes these are built into the analysis tools, but these are 2 dedicated meshing programs, HyperWorks and Qubit, for creating meshes. And I had some cool links there. But basically, you guys have probably, especially the ones at petroleum engineering, have been exposed to probably finite differences and finite volume methods. The finite element method is really a generalization of those. So you might know that finite differences are confined to regular grids, right? Yeah. So you can't have sort of arbitrarily shaped boundaries, right? You can with finite volumes, but you probably know that and I just got 1 more minute, we'll be done. You probably know with finite volumes, if you have a regular grid, the discrete equations are exactly the same discrete equations you'd get if you use finite differences, right? Probably done that exercise before. The advantage of finite volumes is that you don't have to have regular grid. You can go to arbitrarily shaped. You don't even have to have you can have arbitrarily insided polyhedron, right? But the disadvantage is that in a true finite volume technique, right, you have a constant field across the volume. You have no inner volume interpolation. So your only tool to increase the accuracy of the solution is to make the mesh smaller. Right? In finite elements, you have another tool. You can increase the approximation, either by going to higher order polynomials or using some enrichment. Okay? And so what you'll see in the end is that this is actually a generalization of those other 2 methods. So if you believe or you've seen that the finite volume method is a generalization of the finite difference method, well, the finite element method is just a generalization of that, namely a really easy one in that we just assume, instead of assuming a linear or quadratic interpolation across the element, we just assume a piecewise constant interpolation across the element. And then it all falls back to finite volumes. Okay? So it's really just a more general method than. Okay, we'll end there.